Right, I'm going to talk about the exponential function. For this session, I want to prove that e to the power of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on until infinity. And where e itself is a number that is defined by this series 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial and so on, and it carries on until infinity. Now you can see here that you can get this simply by setting x equals to 1. But of course that's not the proof. We want to prove this. Okay, so that means that given that e is equal to this series, I want to show that e to the power of x is equal to the series here. This number e can be obtained if we start adding up these terms one by one using a calculator or a computer. Of course, we cannot go on adding forever because the terms keep going until infinity. But we don't have to if we just want a certain number of decimal places, because each of these terms gets smaller and smaller very rapidly. So after a certain number of terms, it will have no effect for, let's say, if you want a certain number of decimal places, all you need is to add until the terms are too small to make any change to that last decimal place. And you could try adding them up using a calculator, but I shall just write down the value for e 2.7182818 dot dot dot. Okay, so if you find this number on a calculator, this is what you see until that number of decimal places. And if you can show more places, it can just keep going. In order to do this, to prove this series, it helps to look at the motivation, or one of the motivations behind this function, this e to the power of x function. Now think about the problem of compound interest. So that might seem something quite far away from this function. But let's have a look at that and see how this can actually lead on to this e to the power of x. If you think of say the problem of compound interest, suppose that I have $1 in the bank. Now, and suppose that the interest, I have an interest rate of x over 100 in 1 year. Right, I'll drop the 100. I'll just call it the interest rate is x, so x is a certain fraction. So this means that if the interest is only calculated after 1 year, I have a simple interest. Okay, then the sum of money that I would get after 1 year would be the starting amount, which is the principal, plus the interest rate multiplied by the starting amount. So 1 plus x. But suppose that instead of calculating the interest after 1 year, suppose that the interest is calculated every month. Then I have compound interest, and this is calculated every month. Okay, if this is the case, then after 1 month, to calculate the interest, I would have to use, I cannot use x for the interest rate after 1 month because that's for 1 year. So after 1 month, I would have to take x over 12 as the interest rate. So the interest will be x over 12 times 1, which is just x over 12. And then the total that I get after 1 month would be 1 plus x over 12. Okay, so this is after 1 month. And after another month, the interest would be x over 12 of this amount plus the amount itself. So that means that if I do it every month, then this is what I get after 1 month. Okay, then after 2 months, the amount that I would get would be this, 1 plus x over 12 times the interest rate, which is x over 12, okay, plus this amount that I had after the first month. Now you can see that this can factor out, and I can have 1 plus x over 12 in a bracket. So this, if I take this common factor outside a bracket, then this is what I get in a bracket, and I have 2 factors that are the same multiplied together. So this means 1 plus x over 12 squared. Now if I carry on, then after 1 year, which is 12 months, I would expect that this calculation would repeat another, say, 10 times, so it would gain 10 more of these factors. Therefore, the final amounts that I would get would be this to the power of 12. And you will find that if the interest is compounded every month, I would end up with more money. This is something we can easily check if you put in any value for x, let's say 0.1 or 10%. You'll find that if you calculate x calculate this, when x is 0.1, the answer would be bigger than if you calculate it for the simple interest. So this is why compound interest is much better than simple interest. Next, let's suppose that we can somehow convince the bank not just to compound our interest every month, but to compound it every day. So we compound this every day. Now, if we do it every day, then the interest rate has to be interest rate for 1 year, interest rate x, has to be divided by the number of days in a year to find interest after 1 day. So in this case, the interest rate for 1 day is x over 365. Now my starting amount is just 1, so just $1. So this is the amount of interest I would get after 1 day, and I would add 1 to get the total amount in 1 day. And then if I repeat this kind of calculation that I did for the monthly compound interest, you can see the pattern. Alright, after 12 months, this is what I get, and you see that the 12 appears at the bottom of x because we had to divide the yearly interest rate by 12, and it appears up there in the power because there are 12 months of interest to compound together. So in using similar steps, we will find that after 1 year, the total amount that we will have would be this to the power of 365. Basically, we have to multiply the amounts by this factor every day for 1 year. So that's why we have this power here. You see that it's the same pattern here. We have a 12 there and the same number 12 there. Number of days here, number of days there. So this is the correct amount of money that you get if you compound your interest every day for 1 year. And if you again put this in your calculator, you'll find that, say if x is 0.1 for 10% interest a year, you'll find that if for a certain value of x, when you calculate this answer, you will get more money than when you calculate this answer. So in other words, the larger number of periods, the more intervals you use to compound your interest, the more money you'll get. So try convincing your bank to do that. Right. Now let's allow our imagination to run wild and say that, right, I'm going to compound it not just every day, but maybe every minute or every second. I'm going to make the time as short as possible, all right, so that I will compound it over a very large number of intervals over the year. So I compound over many intervals. Compound over, let's say, n intervals. So interval here refers to, for example, the day here or the month there. So suppose I divide the year into n intervals, then following this pattern, I would expect my compound, the money that I would get after 1 year to be 1 plus x over n. Alright, so I would replace the number of days by n and the power here by n. So if we are lucky and we can get a compound interest in which n actually becomes an extremely large number, meaning that the intervals become extremely small, then we'll get the most money from our interest. So even though the bank would most definitely not go along with this, we can always try and calculate how much money we can actually get if we can actually do this. Now let's try and find what is the most money that we can get if we allow n to get really big, as in maybe going all the way to infinity. So what happens if n actually goes to infinity? So let's try and answer this question, and the answer will lead us eventually to prove this series and to the number e itself. So what I've done so far is I've not actually started on the proof for this, but I have motivated using compound interest this expression here that would eventually lead on to the expression for e. So as a first step in the proof, like a step 1, I shall do an intermediate proof. Alright, in the step 1, I shall prove that as n goes to infinity, this 1 plus x over n to the power n goes to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. Now hopefully you can begin to see where the connection, how this is connected to E. This is exactly the same series as this. Alright, so as a first step I want to show that this series actually takes this form when n becomes extremely large. And once I have proven this, I would then do some algebra with this expression and show that it is related to E. In order to show this, we shall start with this expression for say an integer value of n that is finite, that has not gone to infinity yet. So let's take n to be some integer, and then we shall expand this expression and show that the expansion would approach this series when n goes to infinity. So that's the way that I'm going to do it. So for a start, I would need to expand this. Now expanding this requires something called the binomial theorem. I shall prove this in a separate session. For now, let me just write down the result. It says that if I have 1 plus x to the power of n, where n is an integer, then this is equal to 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus n times n minus 1 n minus 2 over 3 factorial times x cubed plus dot 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 until the last term would be x to the power of n. Alright, so in between, the coefficients of each term follows this pattern. Right, so let me write down the expression that I got just now, which is this one. Let me copy out this expression here. So I have 1 plus x over n to the power of n. Applying this formula, I get 1 plus n Now instead of x, I have x over n. So x over n, I need to substitute into the x here, 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 and so on. So that's x over n. Likewise, I sub in the x over n here. Becomes x over n squared plus that becomes x over n cubed plus dot dot dot. Okay. Now I'm not going to worry too much about the last term because eventually n would go to infinity, so there would be no last term. So this is what it looks like using the binomial theorem. Now I am interested in what happens when n goes to infinity. So let's take it one step at a time. Let's not allow n to go straight to infinity. That's always hard to imagine. Let's just allow n to become a very big number. Let's think about what happens to this. Right, the n here and the n here cancels. Okay, so that's fine. 1 plus x plus... Let's look at the n here. Look at the n minus 1. If n becomes very big, then the minus 1, the 1 here, is very small compared to the n. So small that if we ignore it, if we just leave it out, it would not make much difference to the answer. Right? So that's the kind of idea that we would often use when we deal with very big numbers. We can approximately neglect the much smaller numbers that are added to it. So I would say that this is approximately, okay, if I neglect the minus 1, it will be n times n over 2 factorial over times x over n squared. Now let's continue with this reasoning here. I have n minus 1 here, so n is very big. I can neglect the 1. Likewise, n would be very big compared to the 2, so I can neglect the 2. So approximately that would be n times n times n. And that's x over n cubed plus dot dot dot. Okay. And we can now simplify this. A word about this approximate equal sign. It's approximate because we have made an approximation, we have neglected the 1. So it's not, the right side is now not exactly equal to the left side. But remember that the bigger n is, the more equal this would be. And eventually, in 1 or 2 steps later, I'm going to allow n to go all the way to infinity. Then this approximate will become exactly equal. So that's the plan. But for now, we notice that we can simplify this a lot. You see, I have n times n here, and I have an n squared in the denominator. So this can cancel. I have n times n times n, on top, and I have an n cubed at the bottom. So these cancel. So I have 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus dot dot dot. Now let's take a look at what I've written down, or what I was trying to prove. I was trying to prove this, that e to the power x is equal to this. If you have a look at this, compare now this with this, see that they're now exactly the same. Okay, so looks like we are going in the right direction, even though we've not quite arrived at the e itself yet. As I said, if I allow n to go all the way to infinity, the approximate equality will become exact. So let's do that now. If I allow n to go all the way to infinity, then 1 plus x over n to the power n will become exactly equal to this. Okay. I've done the first step in this demonstration, in the proof that I want to make. Let me now go on to step 2. In step 2, I want to show that when n goes to infinity, this expression 1 plus x over n to the power of n, this becomes equal to 1 plus 1 over n to the power of n x. In other words, the x here somehow disappears from inside the bracket and appears in the power. So this is what I need to prove in this step. Right. And here is how we do it. I'm going to say that if I look at this expression, when I'm interested in what happens to this expression when n goes to infinity. Okay, so this value, n would be this value and this value. Now if you think about infinity, it means that n itself is not actually a specific number. It may be a number in the beginning, but at the end, n goes to infinity. So I don't have to call it n, I can call it, I I can just make anything in its place, as long as that thing here and there are the same and they go to infinity together. That's fine. So what this means is that I can, for example, let n be nx. Okay, maybe that's not a good way to say it. I can change n to nx. Okay, then this expression becomes 1 plus x over nx to the power of nx. Right. Now, they are obviously not equal. Alright, after all, I have n there and I've multiplied n by an x here. So for a normal number of n, these two are not equal. But they become equal when nx goes to infinity. Okay, because then this number here goes to infinity, just as that number here goes to infinity. So it doesn't really matter what I start with. I might start with n, or I might start with nx. In the end, they all go to infinity, and it's not a number that you can distinguish anymore. Alright, it's just a thing that went all the way to infinity. Alright, so in the end, those two are infinities, those two are infinities. So therefore, the end result must be the same. So following on from that, I have, when n going to infinity, this actually becomes equal to this. And if I then go back to the time when nx is not yet an infinity, I can do some algebra here. I can cancel the x and get 1 plus 1 over n to the power of n x. Okay. Now, I'm going to... right, okay, no, I don't have to do anymore. And this then is the same as this. So I've proven what I set out to do in this step 2. Okay, so that's done now. I've shown that when n goes to infinity, this turns into this. And in step 3, right, I want to prove that when n goes to infinity, this expression 1 plus 1 over n to the power of nx goes to e to the power of x. So you can see now that I'm finally going to arrive at e. So let's see how we can do this. If I start with this 1 plus 1 over n to the power of n x, think about this n times x in the power. Think about first raising this bracket to the power n, and then raising this answer to the power of x. Alright, this is actually equal to this because we can multiply powers. Next, think about what this is. If we look back at this expression here, right, when n is very big, remember that we've shown in the previous step that this becomes equal to this. Now if I compare this with this, let me write this out separately. 1 plus 1 over n to the power of n. Okay, that's 1 plus 1 over n to the power of n. And here I have 1 plus x over n to the power of n. So the difference is that the x is changed to 1 down here. So this means that if I substitute 1 into the x, I can use this formula to write out a series for my new expression for this. Okay, and that series would be 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus dot dot dot. Alright, so let's just check that this is correct. I've substituted 1 into the x there, so I get 1 plus 1, 1 into the x squared, so I get 1 over 2 factorial, 1 into x cubed, I get 1 over 3 factorial, and so on. And that's exactly what I have now. So this means that, so this is what I get. Of course, n must actually go to infinity first. Now, according to my definition in the beginning, remember, I've said that E is defined as this. Now, if I compare with this with this, you see that this is actually just E itself. Okay, so this is equal to E. So what I have now is actually shown that this, as n go to infinity, this expression becomes E. Okay, so we are getting closer and closer to our final goal. Now let's go back to the previous expression. I now apply these results to that. You see that this, which is this, is just E. So therefore this is equal to E to the power of x, which is exactly what I wanted to prove for this step 3. So it looks like I have completed the proof. Let's look back at the original question and see what is it that we need. We want to prove that e to the power of x is equal to this series, where e is equal to this. Right? And let's look back at what we've done. I've made a step 1 in which I've shown that this expression here is equal to this series, okay, which is the right hand side of this equation that I want to show. Down here. And then in the next 2 steps, I have shown that this expression on the left I've shown first in step 2 that it can actually be rewritten in this form with the x taken out of the bracket and into the power. And then I've shown in a step 3 that it can be written just by separating out the power. It can be written in terms of e as e to the power of x, which is just the left hand side of this. Alright, so combining steps 1, 2 and 3, we have just proven this equation. We'll stop here.